Hi everyone, my name is Jay, and here this video is for you guys about problem set 6, going over some concepts and going over some of the problems and parts specifically. Kind of a disclaimer, even though I am an 802 TA through the physics department and a facilitator through TSR squared, I'm not officially doing it for any of those. So this is not official in any way, in any capacity. But this is just for you guys to work on Pset 6. So the first thing I want to go over is basically an analogy or like a way to think about um, what a circuit is. And so we can really think about it kind of as a roadway. Okay, so assume a circuit loop. Okay, so um, an actual circuit loop, right? This loop will correspond to a traffic circle, if you will. Okay, and this traffic circle is packed bumper to bumper with cars. I'm not going to draw cars, but um, it's packed. Okay, so it's bumper to bumper. The resistanceless wires, right? So here, these wires correspond to level stretches of road with no potholes. Okay, so these things right here. And resistors correspond to downhill segments of road filled with potholes. Okay, and it goes downhill because when you go with the current, it loses potential energy. Okay, and so the kind of analogy here is that the cars are the charges, right? And so the charges are going this way, so current is going this way, right? So as you go with current, as you go with the cars downhill with the potholes, it loses electric potential, and then the potholes are there just to make them flow downhill at a constant speed, no acceleration. Okay, so the charges are at a constant I charges per second. The battery or EMF, right? So let's assume there's a battery here. So this is, hold on, this is all corresponds to this thing. So you have resistance to this wire, then you have resistor, then resistance to those wires again. At this stage, you have, let's make that more level, some car elevator that lifts the car back up to this same level, right? And then the car can go back, and then the cars come back around this way. And this corresponds to a battery, okay? Yep, so the current is just a number of cars passing through the piece of road. So, like this, how many cars pass through this piece of road, dq dt, or d car dt, right? And each car is one charge. When you're talking about potential difference, is talking about the height of the car, the potential energy, right? If you're talking about height, right, of the car. And so across the resistor, it goes down like so, and then up the elevator, it goes up. Okay, and the reason this analogy is helpful is because it can kind of dispel a common misconception, and it's that when you're passing a resistor, the current is lower, right? So if you're thinking about a resistor, right? Let's talk about this circuit. As current goes this way, it kind of makes sense. Across the resistor, there'll be less current, there'll be less charges going across this resistor. But if you think about this analogy, hopefully it'll make kind of some sense. So if you're talking about cars, right, packed bumper to bumper, if you go down the resistor, go down the hill, right, you're going to slow down. But then since, it's, packed bumper to bumper, the cars all across, these cars too have to slow down. And so all the cars are going at the same rate because they're going in a circle, right? So they're going in a loop. And so if one part of the loop has to slow down, the entire loop also does. And so the more physicsy way to explain it is if you have a resistor in which the current at, say, point B is less than point A, then that means some charges are going in. So let's say this is 5 coulombs per second, right? The current is 5 coulombs per second here, and then let's say the current is less here, maybe like 4 coulombs per second. That means that there's 1 coulomb building up on this resistor every second, and that doesn't make sense. And I'll talk more about this in the next few slides, but I hope hopefully this makes sense to people. Just to be clear, raising the resistance does decrease the current. It just does so everywhere. So the current everywhere is decreased. Okay. So again, remember the cars are packed bumper to bumper, and so they can only go as fast as the slowest spot. And in this case, the slowest spot will be the resistance right here. Okay. So that's it for the analogies. Hand waviness. I'll go back to this analogy later on in this video as well. So let's think about some concepts here. So think about this concept question. So consider a tapered slab of conductive material, say aluminum or some other metal, right, with a battery hooked up to it. The battery has a positive end here, negative end here, so the currents will flow like so, right? So into the top and then out from the bottom. And circle A and circle B refer to the imaginary circles at A and B, points A and B, and then these circles that kind of subtend that. Okay, so the question is, which electric current is bigger at circle A or circle B, or are they the same? And explain. So feel free to take a moment and pause the video to think about it. And so again, this is talking about the analogy that I talked about earlier, where does it make sense where the electric current is bigger on the top than at the bottom? And that would mean if you have 5 charges kind of coming in, so let's say this is A and this is B, right? So this corresponds to kind of the circle A and circle B. If you have 5 charges coming in from the top, right, you can't have any kind of buildup of charge in a steady flow circuit, right? So in these cases, we're always thinking about steady flow circuits. And so 5 charges necessarily have to come out of this conductive material. And so the current is the same, even if, charges do build up. So let's say, 5 charges come in and then this one doesn't come out. This, just builds up here somewhere, right? That'll mean every single second, see this is 5 coulombs per second. We're going back to that. This is 4 coulombs per second. It's Q. There's 1 coulomb right there, 1 coulomb. That means that every single second 1 coulomb builds up, but once they build up, right, every single second, they'll immediately repel each other and they'll kind of eject themselves out. Okay, so the kind of answer here is that they're the same. They have to be the same. Okay. Now let's think about the electric current density. Okay, which one's bigger, at circle A or circle B? Or are they the same? Take a moment to pause and think about it and explain it to yourself. Okay, and so we know that from the last part, the electric current at A is exactly the same as electric current at B. But now we want to talk about, the electric density, which is basically how dense the current is. And if you're taking a look at these 5 charges again, if these currents are the same, this area is smaller at B, right? And so we know that J is I over A, right? And so if A is smaller, then J at B has to be bigger, and that is the answer. Okay, now let's move on to a specific problem. So problem 1, battery life. Um, it talks about this kind of mysterious quote, and I'm going to include it here. A D battery has a life of about 10 amp hours. And again, the A is for amp, and short for ampere. So an ampere is the units for current. Okay. Again, current is defined as dq dt, right? So an ampere has units of charge, coulombs over seconds. That should be a C. Okay. And so an amp hour should have units of charge, right? Coulombs. And what do we remember? So again, remember batteries also have an EMF, right? So if you're talking about a battery in a circuit, it has an EMF. So what do we remember about energy, right? So energy, we remember this equation, right? So delta U, the change in potential energy, is Q times delta V. And it just so happens that the energy of a battery, so E of the battery, is equal to the battery life, let's call it B, times the EMF, okay? So the energy of the battery is equal to the battery life, in this case, so this is units of charge, right, coulombs, and this is energy charge units of volts, okay? And that's the equation you want to use for the energy of the battery. Okay, internal resistance. So there's not really much to talk about here, except that, in part A of problem 1, you can effectively ignore this internal resistance because it told you can, right? So this is Ri, and say this is RL. But in part B, you can't do that anymore because now we're lifting it at the fastest rate instead of the super slow speed. And so you just have to take into account that the delta V over this element, or Vd minus Vc, right? Assuming that I is going up, so we're going counterclockwise. I'm sorry, clockwise. Then this V is not just the EMF anymore, it's the EMF minus IRI. So it is epsilon minus IRI or IRL. Okay, that's just the only thing. Okay, now part B also has this kind of cryptic hint saying that you want to maximize power delivery to the winch. Okay, and it's because we didn't tell you the definition of power. So the power that is dissipated over some resistor is defined as this thing. Okay, it's either defined as the current that the resistor experiences times the resistance, or is the delta V across that resistor. Okay, we just talked about this before, right? Across the resistor, not across only the ideal battery, over R. Okay, that's the only thing you need. And then for part C, we might need this definition where power is defined as the change in work done over time. And so in this particular thing, work is defined as the work done on the winch. Okay, so work transferred from the battery to the winch. And so since we're still, finding the max power, sorry, not finding the max power, we are still, continuously at the max power. This is constant, right? And so we know that P over some delta T is just the change in energy, right? And so this is the energy put into the winch. And problem 2 is kind of tricky. There's some negative signs lurking around here and there, and I just wanted to go over that really quick. So assume you have a resistor kind of across here, and this is, let's say, point A, point B. Now we can't measure the voltage difference, right, if there's no current. If there's no current, then that means there's no voltage. So we have to assume there's some current, right? And we want to know delta V across these 2 points. So V minus VA. So just to be clear, this is what we're supposed to be given. We want to find delta V, and they have to give you that it's VB minus VA. So we're going across this way. Otherwise, if they give you delta V is VA minus VB, it'll be different because now we're going this way. Okay, but no, okay, so for now we want to look at VB minus VA. And because it's going with I, right, we know that it has to be negative, right? So negative IR. We learned that in sign conventions in the lecture slides. But what's kind of confusing is that this is exactly the opposite of the voltage gained by the battery, right? So if you have battery like this, and then a resistor, okay, so this is the positive and negative terminal, and so, whoops, I have the current going this way, right? Let's say that's EMF, and then a resistor. So I have E minus IR, the loop, a closed loop is 0, and this is positive IR. And again, the reason is, right, so in this case, you're talking about the, downward slope, right? But this is exactly the opposite of how much the car elevator is lifting you up, right? So in this case, the EMF is talking about the car elevator, the delta V there. And then what we want to find is actually negative of that, how much we're going down. So yeah, hopefully that helps. And basically, so in problem 2 specifically, you kind of have to assume V in, right? And you want to assume that there is a battery there. And this is actually what you're going to do in parts B through D. So let me know if you have trouble with that, and I can help you with that in office hours. Okay, so this is for problem 3, and specifically problem 3D. Hopefully this will help with parts A through C if you're also confused. Right. For specifically problem 3D, it's talking about now you have, again, 2 plates and then some kind of dust that settles on the ground plate. So dust is up here. And then there is gas in between these plates that also offers some resistance. Okay. And the tricky thing to understand here is what they're asking for. So they're asking for the electric field between the 2 plates. So they're asking for the electric field here. Okay. We know it points up because they said that this is 0 volts. So that's a different color. And this is 5 kilovolts, right? So we know that if you gain electric field is positive, then electric field has to point up. Make sense? Okay, so electric field points up. And what they're asking for is the electric field right here, this one. The confusing part about this problem is that the electric field at the gas is actually different than the electric field in the dust. Okay, and I'll try to explain why. So if you graph delta V, over d. Let's say d is 0 here, d equals 0, and then d equals 10 centimeters right here. Okay. We know that as a resistor, we can kind of simplify this entire situation, so this entire thing, into a circuit. So let's say this is resistance wire. We have the resistance of the dust, right? And we have the resistance of the gas, right? So D for dust, G for gas, and then straight wire again. And we know this is voltage at 5 kilovolts, voltage at 0. Okay? And so if you kind of graph this, let's say that you lose some potential here. Say this is delta V of the gas, right? So as you go across this gas resistor, it'll have some potential difference due to that gas, right? So V equals IR. So this is V equals IRG, right? But the resistance of the dust is different, right? So the resistance of the dust is smaller, I believe, so it'll have a less of a what do you call it? Less of a slope, right? Okay. And so this is kind of the graph of delta V. We also know that the electric field is defined within delta V like this, right? And so if we're talking about between these 2 points, I'm sorry, no, use electric field is this thing, right? So if we can find the electric field, the magnitude of the electric field by taking the negative derivative of voltage, if the slopes are different, right, between the gas and the dust, this is IR dust, then that means the electric field has to be different, okay? And so that's the main hint to get here, is that to find the electric field between the plates, that is in where the gas is, we have to kind of first find the current, because we know, as again, using the analogy, right, the current has to be the same across these 2 resistors, or across these 2 resistors, right? However, right, the electric field, or as you say, as we know, it depends on the potential difference across these 2 are different. Okay? All right. As for problem 3E, I think this is kind of a tricky question because it's worded pretty trickily. And so I'll just try to get you started here by rephrasing what it says. Okay? So it says the percentage of particles that escape into the environment, let's call that alpha, okay, is exactly equal to e to the negative beta omega d, where beta is some unknown constant, or it's for some constant beta, and then WD is proportional to the electric field squared. Okay, we know that 0.01, right, or 1% of dust particles escape when the drift velocity is clean. Or so, sorry, when the drift velocity of the clean contraption, right? And so you get 0.01 equals e to the negative beta w clean, C for clean, okay? And now we want to find alpha of 1 millimeter, W1, alpha 2, E beta, W2, okay? Using these three equations and the fact that if the drift velocity is not perpendicular, if it's proportional to the square of the electric field, right, the W of the W of A over W of B, any A or B, is exactly equal to the electric field in that instance over the square of that over the square of the electric field at B. Okay, so using these two things, I squared, you should be able to solve problem 3E. Okay, now problems 4 through 5, 4 and 5, I think you might be able to do. And if you have any questions, again, just let me know. And I'll go through problem 6 in simplifying circuits. So simplifying circuits was never really taught, so I'm just going to go through it really quick. I mean, it was kind of taught, but not explicitly, okay? So simplifying circuits has to do with focusing on two elements at a time and then combining them. And specifically resistors, okay? So if resistors are in series, which means that if there's two resistors next to each other, this is R1 and R2, then this is basically the same thing as one big resistor, right? So R1 plus R2. And we can think of this in terms of the analogy that I said very early on in this video, where, if you have, let's erase this. If you have two resistors or two hills with potholes, this is exactly the same concerning potential energy if you just had one big hill with potholes, right, added together. Okay? Does that analogy make sense? And then in parallel, you have this weird formula here. So parallel just means that if you ever have coming in and then right here like that. So this is in parallel if you have R1 and R2. And so this equals kind of this weird thing if you want to treat it as one resistor. 1 over, right, so the R effective is 1 over R1 plus 1 over R2. I mean, you can simplify this to R1, R2 over R1 plus R2. Okay. The kind of intuition here, if any, if you're trying for that, is that this effective resistance is actually less than R2 or R1 individually. And here is an analogy going back to the cars, why that makes sense. Okay, so imagine you have a one-lane roadway, right, branching into two different lanes. So let's make this like that, branching into two different lanes, right? And then they join back up together, and then they have this roadway again. So this one-lane roadway, all right, is originally bumper to bumper. But once you add a new lane, right, even if there's resistors down there, there's now more room for more cars, meaning two lanes together are less resistant to traffic flow. So basically there's more lanes, right? And this means more cars and more cars can flow. Um, yeah. In terms of batteries, it depends. So I guess if you look at this kind of diagram to the side here, so they first chose this, right? This first resistor in parallel, right? And they made that this resistor here. And then you have two resistors in series, these two, and I added them into this one. And then this last one is adding two batteries together. So be careful because batteries in series, it really depends. Sometimes you can't add them and sometimes you can. And so you can only add them together when they experience the same current. Okay, otherwise known, not known as, but if they are on the same loop. Okay, so in the same loop here. Okay, so if you have something like this, and then like another battery here, then you can't add them because they're on different loops. Okay, because they could experience different currents. But since they are in the same loop, you can add them like so. So if they're facing the same way, if they're like this, and they're E1 and E2, then this just equals one big one, right? E1 plus E2. Okay. Again, so this is, taking the car elevator up once and then twice. It's the same thing as taking one big elevator up the entire way. However, if they're facing different ways, then you need to subtract them, right? So if you're taking the car elevator up through E1 and then down, right? Because you're going against, going down E2, then it's E1 minus E2, okay? And that's how you simplify. You just keep doing that over and over again until you get some simplified circuit or more simplified circuit. Whoops, everything just disappeared. Okay, so this is I2 facing this way, right? Because it's pushing this way. And so if they join up here, then it has to go this way, I3, if that makes sense. But in general, you could just arbitrarily assign it and things should work out. And then again, you want to assign circulation directions for each loop. And so talking about loops, this is also arbitrary as long as you're consistent. Basically, you can choose this loop across and then this loop across as long as you go, through each line of this entire circuit, where I can go this one and this one across all the way like that. It doesn't matter. It should work out using Kirchhoff's rules. Okay. And then again, you want to use the delta V over any closed loop in a circuit is equal to 0 in current conservation. And then there's just algebra after that.